By the way, my name is Kimberly. I work here in the Visitor Center. We have an awesome program for you tonight, starting with Gary and Chris from the IRIS mission. Gary Kushner, by the way, is our program manager. He works at Lockheed Martin in support of NASA for the IRIS mission that launched June of last year in the summer. Previously, he was the program manager for AIA instrument on the NASA Solar Dynamics Observatory, which is currently in operation, so he has got 2 missions in orbit right now. He's also supported the focal plane package for NASA and the Japan Space Agency's High Node mission, and he started in aerospace when he worked on the NASA Fuse mission. So to my left, this is Gary Kushner, or right, your left, Gary Kushner. And we also have Chris Hoffman, who will be talking to you. He's also from Lockheed Martin, and he works on the IRIS mission as the Chief System Engineer. So we got engineers in the house, you guys. He has 21 years experience in small satellite and payload system engineering and integration and testing, and he's worked with mission ops for those 21 years. A lot of missions. He's covered over 6, spanning from SAMPEX in 1992 to FAST, and all these are acronyms. You have to look them up, Google them, okay? FAST in 1996, SWAS 1998, TRACE mission, which is in orbit, I believe, still in 1998, and High Node in 2006. So without further ado, I'm going to ask these gentlemen to have a seat. We're going to give you an overview of the mission and then jump right into some questions about the spacecraft, which is our topic for the evening. Thank you so much. Gentlemen?
Okay, can you hear us? Okay, so we're engineers. I'm not much of a speechifier, so engineers tend to use lots of charts. So we'll just use a few charts to give you an overview of the mission, and then really open it up to questions. It's supposed to be kind of an open forum. If you go to the presentation, the PowerPoint, there we go. What is IRIS? First of all, IRIS stands for the Interface Region Imaging Spectrograph. That's actually our logo up there in your right. We have it looks like a Pink Floyd cover. It's a spectrum. We do spectroscopy and some imaging. We'll go into a little bit of how that works. And all those other acronyms on the bottom are all the other institutions that were participating in this. So this was actually an international collaboration, including Oslo, Norway, Stanford, Ames. So even this is a small mission, takes a lot of people and a lot of groups to put together. And let's see. This is... IRIS is a small explorer out of NASA. These are about 7 feet tall, 4 feet wide at the base, and about 12 feet wide with the wings displayed, the solar arrays deployed. Not a very big satellite, but these are science-based missions. So we're supposed to answer a scientific question. We're not doing weather. We're doing, why does the sun work? How do we understand different aspects of space? Our mission was solar. And so the team built the instrument, the spacecraft. Ames did the mission ops and ground data system. And then there's also a science team to do a lot of the science data analysis. This is a pretty complex instrument. It takes a lot of scientific computing power to understand. Let's go to the next slide. And this just shows the whole mission. We actually have our ground station up in Svalbard, Norway. There's Ames Network. The mission ops and ground network is here at Ames. The observatory is on orbit, and you saw the video of the launch from the Pegasus and the L-1011. And actually, Stanford does the science data processing, and our data is available to the world. All the scientists, you, the public, can see this data within hours of it being generated on orbit. Next. So, this is an imaging spectrograph, which is actually a pretty complex instrument. It can take images of the sun. It can also take spectra. And spectra is how you understand the different wavelengths, the different compositions of the sun. You measure the energy states of the atoms. You'll see that on the left is a typical spectrum. But we're looking at a region of the sun called the interface region, which is very dense. It's between what you see as the photosphere and before you get to the corona. And that's a very dense region, very hard to understand. So they had to have the modeling, computer models, up to a state to be able to understand the data we're going to see. But why are we doing this? The sun itself the sun's kind of surface. I'm going to get up on the ground. The sun's surface, the photosphere, is about 5,000 Kelvin, 5,000 degrees Kelvin. Out in the corona, out in the way out in the atmosphere, it's up to 1,000,000 Kelvin. So how do you get from a relatively warm surface out to a very hot? And when we say hot, we're talking about energy states, corona. And that's one of the big questions IRIS and our other missions have been trying to understand. We're looking at this thin region here. Something's going on. Something's taking the nuclear energy of the sun. There's taking the magnetic field and converting it to a lot of energy out. And we're trying to help, the scientists are trying to understand how that works. Back to the charts. And these are the different wavelengths we study. We have 3 wavelength channels and an imaging channel, and we take this data simultaneously. Next chart. And so this is the observatory. Do you want to take some, Chris? Or
sure.
Okay.
This is the mission summary. We launched June 27th or June 28th, depending on which clock you're looking at. We are a solar pointing telescope, a resolution of 1/3 of an arc second. We image in the ultraviolet, 1,300 to 2,800 angstroms. And as a reference, the human eye can detect about 3,800 to 7,500 angstroms. So this is below what the human can see, and it's also below what is absorbed in the atmosphere. That's another reason why we have to go to orbit to take these images of the sun and these wavelengths. We're a polar orbiting satellite, 620 by 670 kilometers, which is about the distance from here to Los Angeles. So it's not very far up in the sky. It orbits 97 minutes. It's about 400 pounds or 183 kilograms, so double the mass of me roughly. The power is about 300 and it generates about 360 watts. It uses about 260 watts. This is a peak power number that we have on the screen. So we generate a little bit more than 3 light bulbs and use about 2 light bulbs of power, old school light bulbs. The recording capacity is actually 48 gigabits. It's a space qualified hardware, so it's rad hard. Consequently, what we put on orbit is about 1/2 the smallest iPhone storage that they're selling on the market today. But because it's radiation hardened space hardware, we don't get to put as much up as we have in our pockets. It's a 2-year mission. We're hoping that it gets extended for 4 years at minimum, and with funding luck, maybe we'll go to 6, 8, 10 years. Okay, next chart, please.
That's a well-placed size, actually. And just to go a little bit, I won't go too much more into technical, let you guys ask questions, but this front end is a telescope, just like what you can have in your backyard. It's obviously a little fancier. This is the primary mirror. That's the front door that points out to the sun. And we take the light from the telescope, and then we put it into this device, which we call the Spacecraft. And this has multiple channels and allows us to look at the sun in the multiple wavelengths that we've been talking about. And back here are 4 CCDs, just like in your camera. But your camera, these are about $1 million a piece, scientific CCDs. A little bit more pricey than yours, but they're also designed for space application and for obviously very high resolution. Next slide. That's me. And that's a picture of the telescope section itself. And also there is this other little telescope on top that's called the guide telescope, and we actually use that to point to the sun and to know when we're pointing on the sun or off the sun. So that gives us a little air signal if we're wiggling off the sun that sends a signal to the spacecraft, hey, put me back on the sun. So it's like it's a much smaller version of a telescope. Next. And then that's the spectrograph assembly. Next. Let's show you the spacecraft. Go ahead and next slide. And that's the telescope assembly fully assembled. You'll see these different colors. This white is actually a radiator. So even though you're in space, and you hear about space being very cold, when you face the sun, you actually get pretty warm. And we have to reject that heat. We want to keep the whole system at pretty much room temperature. We design it to work at the temperature we build it. And so you have different colors on there to control the heat. We'll then cover this all with those blankets you see. So you'll see one of the pictures will all be shiny, and that blanket helps us, just like a blanket at home, maintain a constant temperature. Next. And then telescope's great. It does the science. It does your imaging, but you have to point, you have to produce power, you have to produce the memory, you have to get the data to the ground, and we have what's called the spacecraft bus to carry out all those functions. And this represents a spacecraft bus. It has lithium-ion batteries, so we're a little more up to date than some of the older spacecraft. It has what we call an IAU, which is the main computer for the spacecraft. The instrument itself has its own computer, and then we have this is the transmitter. This is the X-band. So this is what delivers our science data. It converts our science data into RF frequency, which can then be beamed down to the ground. We'll also have an S-band antenna to do lower rate data. So this is higher rate data. We have lower rate data. And there's other various features. We have a whole system called attitude control, which keeps us pointed, allows us to move, and various components of that are what we call reaction wheels, torque rods, various features that feed into the system that knows where it's pointing and how to move it around. So that's kind of an overview. Go to the next slide. I think that was kind of the general overview of the mission, the telescope, the spacecraft, just kind of give an overview, kind of hopefully generate some questions. Do we want to go ahead and open up to questions?
In fact, when you do have a question, we have a microphone stand right here for you so that we can hear you clearly. And I'm sorry about the squeaky, we're working on it. Little mouse is running around in here. So you told us about the spacecraft, but I'd like to kick off maybe a question about how unique is the spacecraft's capabilities. Could you explain that a little bit?
I'll talk about the spacecraft. It's actually quite typical. The suite of components we have in the spacecraft is quite typical of a lot of spacecraft. One thing that is unique is that IRIS does not have gyroscopes. Gyroscopes are typically used to take a 3-axis stabilized spacecraft like IRIS is. For example, Hubble Space Telescope uses gyros to slew across to various targets across the universe galactic plane. IRIS does not need a gyroscope because it only does one thing, and that's point at the sun. So its sun sensor is good enough to find the sun. The reaction wheels generate momentum, which turns the spacecraft to the sun. It stays there for the mission. And we have another the guide telescope, which actually is the fine-tuning attitude sensor. And we have a star tracker, which helps us determine looks at the star field in the sky, and that allows us to roll. So we're similar in the sense like Hubble uses the star tracker for attitude updates. It slews across the sky based on its gyro sense of rate, and then it gets an attitude update with the star tracker. Well, IRIS does that too, but since we only look at one star, we don't have to. We were able to remove some of the hardware from the system and save some cost. So that's one unique feature.
Yeah, unique. I mean, what is the uniqueness is how small it is. It's very small. It's only 4 feet diameter, 18 inches high, and has pretty much, except for the gyro, the full capability of the spacecraft. So that's kind of what makes it unique.
The primary barrier, heat rejection. On our previous telescope's AIA mission, we flew some very sensitive entrance filters to block down the full solar spectrum coming in, to pull out just the wavelengths of interest. On IRIS, we actually bring the whole solar spectrum in, and the coatings in the primary mirror allow the ultraviolet wavelengths to pass through. Everything else is rejected as heat through the glass. So it just goes into the glass, gets absorbed on the cold radiator that Gary pointed out earlier, and just dissipated as heat.
So actually, if you meant observatory, not spacecraft, then the point I pointed out, these are dead. Okay.
Yeah, it's a little squeaky. This one's really better. Sorry about that.
No problem. So if you meant the whole observatory, then what I point out is the spectrograph. That's what makes it very unique. That's what does the science that hasn't been done before.
Okay, so anyone else have any questions? Please go right up to the mic, sir. Thank you.
What are the torque rods and how do they work?
Okay, can you bring back the picture of the bus? Do you want to explain it?
Sure, I will. Well, quite simply, the torque rods are, the sole purpose is two purposes. After we separate from the Pegasus vehicle, the torque rods are used to dampen the body rates. So we're tumbling at about 2 to 4 degrees per second per axis. And the torque rods, with the magnetometer, we actually sense the change of the magnetic field. So the attitude control system is torquing a rod on, which kind of like applies a braking force to slow the tumbling down. In the science mode, once we've found the sun, the torque rods the sole purpose is really just to unload momentum from the reaction wheels. So for every slew maneuver about the sun, the wheels build up some momentum. To point, we have to spin the wheels up, and after maybe a couple orbits, the wheels also absorb other disturbance torques, but the torque rods are used to energize the torque rod. It puts a braking force using the Earth's magnetic field, and then at that time the braking force is applied, the wheel is able to spin down to its normal control regime.
So they're electromagnetic then?
Yeah, they're a coil.
Okay.
They're these rods, they're a fiberglass rod with a wire wrapper on it, and so you energize it, it acts like a solenoid, and then it tries to line up with the Earth's magnetic lines. Closer? Okay.
So it looks like you're three-axis stabilized. So what are the pointing requirements for the bus and stuff?
Well, the attitude control system points to within 5 arc seconds, and it does more in the order of 2. It's pretty good. Yeah. And then we have the secondary mirror, the image stabilization system, which then takes that 2 arc seconds and puts it down to about 2 100ths, 2 1,000ths? No. 2 100ths, I believe, an arc second. Or 0.2, or 2/10ths.
That's really good. Thank you.
Yeah, it's a feature we mentioned. The secondary mirror actually has little PZT actuators that can move it around based on the signal.
Anyone else?
So why do you launch do you call it a spacecraft or satellite? Is it the same thing? Why do you use the Pegasus? Versus if you launch it like a rocket? Is that, I'm trying to think, is it because you're trying to, so that it will go in an orbit? Is that?
It's money, size, volume. So when you design a mission, so we could launch. It's not mandatory. I'm sorry. It's not mandatory that you launch from the Pegasus. It has to do with the size we're at. So you see the giant Atlas. We could launch on one of those, but those are more than $100-something million. It fits the small explorer profile. It costs less, and that's the main reason. When NASA, so when we're selected, they don't have a launch vehicle selected. And then afterward, they then put out a bid for launch vehicle, and the one that fits the mission best is then selected. Did that answer it? But it could be launched off, other missions can go into polar orbits too. Now, where you launch from matters. So Vandenberg is the best place to launch, or Alaska for polar orbits. So when you launch from Cape Canaveral, you tend to go more in equatorial type orbits. So where you launch actually does matter.
Because I was thinking if you launch from above horizontally, it will go into orbit easy.
It saves, once you're above, the airplane's at 40,000 feet. And when a rocket's launched from the ground, once you're at the 34,000 feet, they're kind of equal. So what you're doing with the airplane is you're saving all that fuel to get up to that height.
Because once they're up there, they can, rockets can then point and go where they want.
And do you figure out why you were saying the interface is colder than outside? The interface region is the chromosphere.
Transition region is cooler than the corona.
Right. So have you figured out why that is? Or are you still trying to get more data?
So actually, to pitch the next one, Carl Schreiber, one of our scientists, will be giving a talk. But what they do know is in the sun, there's nuclear energy, and it creates plasma, and the plasma will move. And when you have plasma moving, you create magnetic fields. So they know there is twisting of magnetic lines that somehow is then transferring. When they snap or reconnect, they create a lot of energy, and that's being transferred out to the corona. So they know that that's happening between the plasma moving in the sun and the corona, but they don't know exactly how that transition between the magnetic field lines and the energy being released. That's what they're trying to understand. So there is quite a bit of knowledge. There was actually one simulation where you saw it look like spaghetti coming off the guy's head. Those are actually the magnetic field lines that they're trying to model. And what the scientists do is they take this information, they take their computer models, they run hundreds of millions of CPU cycles and try to emulate what we're seeing. Bad habits. Next. Did that answer that question?
The region that's colder,
well, there's the chromosphere, the photosphere is what you see as the visible edge of the sun. That's 5,000 Kelvin. And then you go through the chromosphere, and then out in the corona, it's up to 1 million. And that, when you say temperature at that point, you're really talking about energy states of the atoms.
Eventually, should run out of it. It's helium or helium? I think it's helium.
The sun is helium burning. The sun is hydrogen, and one of the products is helium. There's other, as the sun burns, it creates helium, and then other elements, iron, and other elements.
So how much longer?
Here we have 4.5 billion years, 5 billion years left to go. Next.
How much of the spacecraft is off-the-shelf hardware that you can reuse, and how much of it being designed from scratch?
Okay, if you could, can you pull up the PowerPoint again? It's easier for me to be visual. So, and when you say off the shelf, again, this is space hardware, so of course, you're not going to Radio Shack, you're not going to. Now, there are, the CubeSats, they actually are, but for us, we still have to meet some level of space qualification. And what NASA does is they have different risk qualifications. So Hubble or JWST, that's their highest classification. Those are billion-dollar class missions. Those really can never fail in orbit, so they're held to a very high standard. We're what's called Class C/D, and we're allowed to relax some of the standards, but we still have to meet up or down? Down? Up. It sounds loud to me. So we can use a little bit lower grade, but so when you say commercial, like the torque rods, we can call up, they changed their name so often, it's now United Technology at UTAS. We can call them up and say, we want model AA or whatever, the torque rod, and they'll say, great, we'll have it ready for you in 12 months, send us $500,000. Reaction wheels, these are called AA's, we can call them up, and I'm saying how, it doesn't always work that way, sometimes they drop lines. We call them up and say, we like the AA wheels, we're making another mission, can we have those in 15 months? So that's kind of how we call it commercial off the shelf. The IAU is a company called Broadreach. That's a catalog item. You can say, I want that, and I want it with these cards, like you buy a computer, and we're going to have this size solar arrays, and they'll build that to your specs. So that's semi-custom. Why don't you go ahead? Yeah, definitely.
I'll just summarize by saying everything on the screen is off the shelf, except for our antennas. Our antennas were optimized for our orbit and our seasonal variation when trying to get the data down to the ground. So that our antennas were optimized for our orbital profile. Everything else is off the shelf except for the bus itself that we actually made. So we, Lockheed, more often than not, buys stuff off the shelf and we system integrate to make the spacecraft bus. So.
Much better. But yeah, the bus is machined per our specifications, the structure.
When you spoke about seasons, it caused me to realize, I think in 2 years or something, maybe 16, we're due for a solar eclipse. What will that do to your project?
Good question.
Oh, the eclipse is where we extract a lot of good engineering data for the scientists. Is that what we're talking about?
No, I think you're talking about when
eclipse season?
No, not eclipse season. When the Earth, when the sun is eclipsed, when you and I on Earth see the sun eclipse. Because I don't think that affects the spacecraft at all, does it? Not that eclipse. You're talking about the eclipse, like when you and I go outside and put the funny glasses on.
No, it doesn't affect it because from our perspective, we see an eclipse. Iris is 600 kilometers above, so it sees a different perspective. It might see a little bit of an eclipse that might cause a little bit of we might drop down in attitude mode if it doesn't rely on the defined sun-pointing sensor, but the impact is very little.
We actually have our own eclipse season we have to worry about. So I think it's because we presets, we kind of wiggle in the orbit. So we actually fall, for about 4 months of the year, we fall a little bit behind the Earth, but for a different reason than the eclipse you're talking about. So.
Okay, I'm going to keep it going. You need to have more questions. Hopefully this will generate. That was a good question, though. What about solar flares? How does that affect the spacecraft? Just saying.
That makes us happy. That's what we're there to study. We want to capture them, but so it depends on if the solar flare. First of all, that is what we're there to observe. We're to observe these events in multiple wavelengths so the scientists can recreate it. But as far as affecting it in orbit, if it's big enough that it ejects material, we might see some noise on our detectors. So our detectors would pick up some electronic noise and we'd see snow. But I don't think other than that.
Solar flares generate a lot of papers where the normal stuff sometimes goes into the bit bucket.
Yeah.
So it really gets a lot of attention and a lot of study from the scientists. And one of these explosive events is where we really learn about the dynamic processes in the sun. So it's where they extract a lot of information.
But as far as the health of the observatory, it has minimal impact.
Good.
Would IRIS be able to predict a coronal mass ejection?
So the observatory itself will observe it. The scientists are the ones we hope can predict it. I think right now, that's what we're trying to advance, this data. So if they get the computer models to understand the sun, they can hopefully eventually get to the point to predict that. But right now, it's leading us up to that capability, hopefully. But I think, is there anything else I can say, Jake?
No, I think some of the data does lead to the fundamental science that leads to predictive tools, and there are predictive tools available now. Every week we get a solar forecast update. It's available online, and TRACE, that launched in 1998. They did the same type of fundamental science, understand these magnetic connection events, the explosive events. So this whole body of investigation that has evolved over the past 25, 40 years, combined, that's one of the goals of NASA's heliophysics division, is to be able to predict space weather and predict coronal mass ejections. So we're just a part of that.
Spacecraft going to stay forever?
21 years. Yeah, actually that was one of our design challenges. We wanted to get high enough in orbit, high enough in orbit to get a lot of data down and to stay up there. But NASA's got regulations, or there's actually international regulations that say when you launch, you have to come back in within 25 years, re-enter to keep space junk from accumulating. So one of our challenges was find that sweet spot in orbital altitude that was not too high that we wouldn't violate international policies, but also be high enough that we can do the science we wanted to do. Actually, the orbital altitude affects how many months out of the year we can observe the sun. So IRIS will go into 3 months of eclipse season where we're going in and out of the Earth's shadow. So we had to find the sweet spot. And it turns out we'll be up to 21 years.
I was wondering about the primary mirror. What's it made of? What kind of coatings? And who made it?
Okay, I think I can do 2 of the 3. The mirror is made out of Zerodor, and I'm spacing on the coating at the moment.
The coatings were done by Acton? Right?
Yeah, Acton did the coating, and the mirror was built by Tinsley.
No, I think it was...
Sejam in France. Sorry, some days the memory isn't as good as the others, but I can't remember.
I just had to cost it for another program.
Yeah. So we competed, but Sejam in France built the mirror. But I can't remember what the coating is at the moment.
Well, it's a custom design coating that we developed. We wrote the prescription, and then Acton did the development and testing and the fabrication, the application of the coating. And in 2 weeks, Dr. Untitled will be able to answer that question much more thoroughly than we can. He's our expert.
Yeah.
All right, anyone else? Yes, go right ahead. Okay, got a line.
Have you experienced any significant hardware or software failures, and if so, how have you troubleshooted?
How much time do you have? Well, anomalies, not failures, because a failure is very bad. Go ahead.
There have not been any failures.
Yes.
This has been a very well-behaved mission, more so than I've ever been a part of. The spacecraft computer is not even rebooted, and here we're almost a year into the mission. We've not had any hardware failures. There's some curious things we've learned about the star tracker performance. For example, we're picking up a little bit more light from the Earth when we go over Antarctica, when we're rolled at a certain angle. So there are things we kind of knew would happen, and we're seeing some of it, and we're actually, since we don't have very significant problems to fight, we're actually trying to make things a bit better. So we are putting up some code to improve the star tracker performance based on what we see, and we might do another spacecraft flight software update just to make performance a little bit better. But if we did nothing, it would just be fine.
But we do have the capability of loading software as needed.
What's the bandwidth on the for upload?
Oh, this is one of my regrets, actually. It's 2 kilobits per second. And I wish it was more on the order of like 10 or 15, because getting up a spacecraft load takes about 16 10-minute passes, or about almost 3 hours of upload time. So we break it up into the course of a week to get that load up there. So lesson learned, I came from a mission that, 2 kilobits per second is everything we always ever needed. And that was our baseline design, and the baseline got put into the transmitter design, the receiver design, and then once software in 1998 was much less complex and smaller than software capability in 2013, 2014. So I wish we had more uplink bandwidth. But
thank you.
We're making do.
Okay, any more questions? Feel free.
In regards to the attitude, you guys obviously completed an onboard attitude. Is there any comparison to like a ground-based attitude? A lot of missions fly dynamics facility with Goddard. I used to work on EUVE, so EUVE had an onboard computer to compute its attitude, but then we compared it to an actual ground-based down at telemetry, like the star trackers, of course, find some sensors and come up with a definitive attitude, and then determine whether or not the onboard computer is actually doing its job right. They do that for these smaller satellites.
We actually don't do any post-processing on the ground. I mean, we're fortunate that we're looking at solar targets, so we're able to do the co-location of the solar feature with another observatory, such as SDO. So we do some of that cross-calibration with other instruments to understand how our roll, if the star tracker says we're rolled at 45 degrees, how accurate is that? I can't give you an exact answer, but we found that it's actually very good. What we integrated and measured on the ground, we did little changes on orbit to optimize it.
And then, how long does it mean once the vehicle's up in orbit? How long does it take you to go through your in-orbit checkout for a satellite of this class?
Well, we comfortably made it within the typical 30-day checkout period. We were actually the bulk of the spacecraft checkout was done pretty much in 7 days. And then we waited another 2 weeks while the instrument outgassed before we opened up the telescope door. And then once we opened up the telescope door, then there's instrument calibration. And that probably went on for another 4, 5, 6 weeks.
Thank you.
What are your backgrounds and what path led you to design the spacecraft for
Well, I started out in mission operations. Actually, out of college, I started on an old satellite called IUE. It launched in 1977. So I got my feet wet in mission operations. And then, as I was laid off, 22 years old, a new program called the Small Explorers was starting up right down the hall. And the Small Explorers, which is what IRIS is, was NASA's small program, quick to orbit. So it allowed me to get a lot of quick experience doing a lot of different things, systems related. My degree's in aerospace engineering, so I was kind of geared for systems type of a career anyway. So I just jumped from program to program at Goddard and latched on with this group here in Palo Alto after the Trace launch. And fortunate to do the same type of job on IRIS that I was familiar with, so landed in a good spot.
So let's see, I have a bachelor's in physics at the University of Colorado. I was lucky to be a lab rat while in school, so I was an intern. So I kind of interned into it, putting together vacuum chambers, and then helping the grad students do their sounding rockets. And then just about when I was graduating, the group I worked for won its first satellite. So I was able to stay and work and learn how to do optical testing and then integration tests. So I kind of came up through the integration and test, which is where you put all the components together, test them, make sure they perform as expected. When that mission launched, we're kind of nomads. When the mission's over, you have to go and find your next mission. And that's when I found through a job at Lockheed Martin in Palo Alto, came out here and found out they did similar types of programs. And kind of found my way into systems engineering on Inode with Chris, and then moved into program management deputy on AIA, and then into program management for this. So kind of through the labs in different ways.
Wonderful.
Can you explain what exactly is going on? Is it there's a spectrum or was it prism? So there's the spacecraft is taking the light from the sun and then trying to separate them. Is that what's going on there?
Well, yes, that's the logo, and logos are where we have a little fun. So sometimes you'll see animals. This is kind of our mission patch, but it does represent what the mission does. So you do see the edge of the sun, you do see little features, and of course we don't use what are called prisms work in air and work in kind of visible to light UV. What we work in is what's called the far ultraviolet and near ultraviolet, which is not visible to our eyes, doesn't make it through the atmosphere, and we use what are called, actually if you pull up that graphic, you had the right one. Yeah, there you go. We use what's called a grating, a diffraction grating, which if you, now the CDs are getting old, I'm really feel old. When you hold the CD up to light, remember you can see colors on the CD, a CD, a little disc, or scratches, you'll see colors. We have gratings inside our spectrograph up here. And so the sun comes in with all its wavelengths that are passed by the primary mirror, bounces off these mirrors, hits the gratings, and then that breaks it into its light. So that's kind of a humorous representation of that, but that really is what's going on there. You can pick different wavelengths, and we pick the 4 wavelength regions we want to study, to put those onto the CCDs. CCD, Charge Coupled Device. These are what's inside inside your digital cameras or your cell phones, little versions of this. And those are electronic semiconductor devices that convert the light into electrons that can then be read by computers.
So how do you use that information? What exactly? I mean, how can you?
If you guys, I can pull. We have a video with some of the science data on it, and maybe you can cue that up and then come back to that. But we'll go to your question first, and then come back to that.
I've heard that most CCDs are very good with infrared, and most lenses are bad with ultraviolet, and CCDs are bad with ultraviolet. Do you have a special CCD, or did you do anything special for it?
CCDs have moved. When I started, CCDs didn't do ultraviolet, but they have moved more and more into the ultraviolet and X-ray. So we didn't even have to do special coatings. Now what we do is what's called back thinning. So they are more than just the CCDs you have. What they do is they actually take a normal CCD and they come in from the other side, they shave off the material, and that exposes the material that is sensitive to UV photons. So we don't have to do anything extra special coatings or anything beyond that.
And I'm going to ask a question about the mission, but I just want to also give the folks in the audience another chance, as well as you as well, for last call on the beverages before we continue on with the last part of the discussion. So if you want, don't all leave at the same time, but definitely if you're in need of water or anything, please feel free to go back to the bar. They're going to stay for you. But let's move on, because I definitely want to know more about the spacecraft itself. Someone asked about the design and challenges, what they called failures. I'd like to actually talk about, how long did it take to design the IRIS spacecraft? And if you could touch on maybe some of the challenges for designing that.
The time period, so I don't know if people know how missions are done. I'll give you a little background. NASA has a branch of science branches that want to expand on science. And so what they do is they put out announcements of opportunities saying, we're ready to put something up in space. We want to do something in heliophysics. Now you scientists tell us what your ideas are and how you're going to do it. So we all sit there and we spend time writing these proposals saying we're going to answer these scientific questions and we're going to do it this way. And we submit them and they review them. This one, they down-selected to 6 people. Then we compete with them. We give them more detail. And then out of that group, you're selected or not. And we, fortunately, were selected this time. That process alone started in 2007. And from the time we submitted our first proposal to the time we were awarded was 2009. So we had 2 years into it, thinking about it, kind of spending our own internal money developing these. NASA then awarded us. So we started officially in September of 2009. So from 2009, we started design. We hold a bunch of design reviews to move on to different phases. We designed, so we were awarded in September 2009.
It's about 15 months.
15
months from the time the money shows up to the end of CDR is the design phase. But what Gary was talking about was what leads up is the conceptual, the proposal for IRIS. For IRIS, we proposed this once before, and it wasn't selected, and we dusted it off, made it better, and proposed it again. So by the time the first proposal gets submitted until we actually get money, that was about a year or so?
Oh, from the concept study report? That was about a year.
So it kind of occurs in phases. So I was doing real online research. Its comparison point, Hubble took about 44 years to go through its conceptual development. Of course, it's a much bigger scale, but the thing about SMEX is it's got to be fast and it's got to be cheap, and we reuse a lot of stuff, so we're able to do it in a much shorter time scale.
So 15 minutes to design, and then total development from design to launch was about 45. So that's
really?
And that's a pretty quick mission.
That's crazy. Okay.
Was there any contribution
contributions from the open source community? I don't think I could use any.
Well, I mean, we do, for example, it shows up in ground systems. For example, we use a lot of open source code on ground systems. The whole command and control system is considered open source. It was originally developed by NASA Goddard, but now it's free and available to everybody. So us as a cost cap mission, we took that free software. It's open source. On the spacecraft, it's pretty much all custom software.
Customer reuse.
Well, off-the-shelf software, like the Star Tracker has its software, but it shows up on every Star Tracker that a mission flies with that particular design. It's not one of our requirements from NASA to incorporate. We incorporate small businesses, but not necessarily open source code.
Do you use any test prototypes to be broken for qualification, or is it only a single spacecraft that is used for testing, ground testing, and then flight?
But on a small mission like this, we minimize the number of prototypes, but we do have some. We're called proto-flight, meaning a lot of it is built and flown as is. But the spectrograph was new for us. And that one, we built we call it brass board, which means we're not going to fly it or test it, but we're going to kind of practice how to put things together. We're going to kind of learn how to align it. So we did that for the spectrograph, several electronics boards. Most of them were reused, but the ones we built new, like the power board, we will build a brass board of that, test it before building. So very selected items. Whereas on a very bigger mission, where we actually have a sister mission in our building, they'll build a complete test unit, test it, vibe it, qualify it. But we're a quicker, lower cost mission, so we will do it only in the areas that we feel we don't have enough development.
That was one of the things we had to do to reduce costs. We would have loved to have a structured model, but we chose not to reduce our costs, and we knew it was high risk, but it worked out.
I had another question about what you call the bus. In one of your last slide, you showed the big metal piece, I think, at the beginning. Is it the usual way to do these buses for the spacecraft? Or?
That bus it's made out of aluminum, not carbon fiber, and that was literally a giant, it'd probably take a few minutes to pull up, but that was literally a large, probably 5-foot by 4-foot cube of aluminum that they literally just machined out. We thought that was unusual. We went to them saying, well, why don't you just cut them out and build little modules? And the vendors told us it's now easier to just machine it out of a single block. That's called a billet. And they told us that's how they do it now.
It's feasible on a spacecraft of our size, but a much larger spacecraft, they typically have composites, and they're like bolted together.
There you go. So this is what we're talking about.
Yes.
So that's the bus when we got the metal from the shop, and here it is. And so this is at a vendor. They just have a big giant CNC machine that's out there 24 hours a day milling it. And if it at any time broke, we'd have to start all over again. Small bits. There was one part we made a mistake to fix, but pretty much if it had broken a piece, we'd have to start all over.
Yeah. I mean, I know that now with the machining automation, it's quite easy, but is it less expensive?
The vendors said this was, for the bus we were building, was the cheapest way to do it. We actually had a more complicated design, and they told us, so we were going to build each one of these little modules and then bolt them together. And they said, that'll cost you so much more that this will be the quickest way. So we were actually surprised. So we learned something.
Plus we had a lot of mass margin. The instrument itself is pretty light, so we were able to, we know the orbit we want to achieve, and we realized we had a lot of extra margin, so we gave up some of the mass by choosing this heavier design. It's cheaper, quicker.
And I have another question about the heat management. You talked about it quickly. Can you give us more details on the heat management system in the spacecraft?
Yeah, probably the best way, if you can actually go back to the PowerPoint. I'm trying to think of the picture where the solar is deployed. That's kind of the best way to show.
If you keep going forward, I believe.
Yeah, go forward. gone. There we go. There we go. So, there, perfect. So this is actually Iris with solar deployed. Now the one thing missing from this is the blankets I told you about. So you would see shiny metal, what we call multi-layer insulation blankets. There are about 13 or 15 layers of different materials, shiny material, separating material. That gives you, just like your blanket at home, protection. You'll see different materials. I mentioned the white. This is a special white paint that's designed to give off the heat that we want to reject.
It's only a partial radiator. We had a much larger radiator that's not. We added later.
Yeah, and there you can't see it. Of course, one thing is, so we want to keep this telescope tube at room temperature, 20 degrees C, 70 degrees Fahrenheit, and we actually have little heaters. Again, they're probably hidden, but they're little foil. They're like aluminum foil with wires in them, heaters. And those are, I think there's one here, one up there, and then there's a few in the back here. And those take power from the solar rays and add heat. And so we want to, it won't stay in one temperature by itself. So we have to have heat in some areas. The sun's putting heat on the primary mirror, but the rest of it is trying to cool down. So we actually have little heaters that we have a software program that watches it and adjusts the heat. But the CCDs, the little detectors, you do want to get cold. When you cool them down, they have less noise. And so you can't see it here, but in the back there's a big giant piece of metal we call a radiator. And it's painted white like this. And what that does is that's facing deep space, which is nice and cold. And that's pulling our CCDs down to about minus 60-something degrees Celsius. And so that's kind of our system. We have heaters, we have blankets. The radiators are all passive. We don't use what are called heat pipes. So we use passive radiators, active heating system. Does that give you enough of an overview? But the
spectrograph has a lot of heaters on it to keep it nice and stable where all those sensitive optics are, to keep the optics from tipping and turning and destroying the images. So we put a lot of care into the study of the spectrograph, how it responds to thermal loads.
Yeah, we're so sensitive that even just slight thermal changes will bend and move our optics, and that will ruin our imaging. So we have to keep that.
Keeping it stable to within a degree, the spectrograph itself.
Fourth question. What you mentioned the lithium-ion batteries that were quite new as technology. I understand. I'm not familiar. What kind of additional challenge do they give you, and why?
Let's see. Do you know much about lithium ions?
Go for it.
I'll say a little, and you correct me. You have them on your cell phone. We carrying around with us our cell phones, our laptop computers, the Tesla. Those are all lithium-ion batteries. Ours are very similar. We use the same standard style. What it is, the problem with lithium-ion is aerospace is getting more experience with it. We're, I think, only the second or third Lockheed satellite that's flown with lithium-ion. So some of it is just experience. We're learning how to use them. Each battery has a different characteristic of how you charge them, discharge them. Batteries are actually a very high source of energy. If you short them, they can basically weld. So if you aren't careful with them, they are very dangerous. They can create fires, they can create small explosions. So a lot of it you have to handle them carefully. But compared to older technologies, the old technologies, you had to keep a very certain temperature, you had to discharge deep, you had to recharge very carefully. In that sense, lithium ions are kind of nice. They don't need those deep, like your old chargers, you had to drain them down. These are much more like your cell phone batteries, where you can abuse them a little more. But they do have a very high energy capacity, and that's one of the things you have to be very careful of. And so a lot of the safety rules are kind of new too. So when you transport them, you have to be very careful. So it's more just how to handle them as an issue, but they themselves work very well.
Work at Lockheed Martin in Palo Alto, and so it was 2 years before you could apply to get a NASA grant. What other work do you guys work in at Palo Alto related to heliophysics?
In our group, we're kind of a subgroup of the Palo Alto Advanced Technology Center. We've been doing solar and astrophysics for before I was born, but for 30 or 40 years. So this IRIS mission is the one we are just launched. Prior to that, we launched AIA and HMI on the Solar Dynamics Observatory. If you ever see full disk images of the sun doing great things on YouTube, that's off SDO. Before that, we did Inode, which is on the, we did the focal plane package on Inode. So our group is doing what's called SUVI, which is on the NOAA GOES satellites. Those are operational systems that monitor the sun on a daily basis. So that's what our small group is doing, but we have the ATC do even more missions. We're actually doing one program on the JWST called NIRCam. We have GLM, which is the Global Lightning Mapper on the GOES and NOAA satellites too. So we're the branch of Lockheed that does research and development type missions, not the big communication satellites that's done in Sunnyvale or your military type satellites. So that's kind of our niche, is the more researchy type.
So I know once the spacecraft launches, you can't ever touch it again. It's up there. So what do you do to test it? So get to that level of competence that it's actually going to work once it's up in space.
Put up the chart?
Yeah.
It shows every
chart. Can you go ahead and bring up the charts again? You're a heavy IT guy. Let's just see if we can the chart. Go ahead. Keep going. That's the series.
Go back chart.
Great.
Actually, go back one more chart, please. Yeah.
So you can see it.
Yeah, this pretty much just shows the integration process. The telescope gets integrated in the spacecraft bus. We go to what we call a functional comprehensive performance test. So we test every function that it does to set a baseline before we go into environmental testing. And if you go to the next chart, please. So once we complete our comprehensive performance test, the functional test, we go into, is this in the right order? We did vibration tests first. So this is simulating the Pegasus launch vehicle loads into the satellite. And then the launch vehicle team actually came up and we do what's called a shock test. We actually put on the launch vehicle interface. It has a clamp band around it that gets fired with an explosive bolt. So the explosive bolt fires, the launch vehicle piece drops off and it imparts a shock into the spacecraft. So vibration shock, then we go to electromagnetic interference, electromagnetic compatibility testing. This is to make sure we're not putting out any harmful frequencies to the launch vehicle that would affect it in its flight. And we actually found that we were very quiet electronically. So this test makes sure we don't interfere with the launch vehicle, but also makes sure we don't interfere with ourselves. All the different computer boxes talking back and forth. And we were actually pretty quiet. Then we go into a thermal vacuum test, where we go to the hot and cold survival temperatures that we'll see on orbit. Plus, we also go through a series of about 8 cycles just to kind of qualify the hardware. There's a lot of study in the industry about doing thermal cycles to root out premature failures of hardware. So the industry has kind of concluded 12 is about the optimal number. So we do, we broke that up. We did 4 at the observatory level, but at earlier levels of assembly, we actually accomplished another set of thermal cycles. Then we come to the final comprehensive performance test, just to make sure that the performance, the optical performance, the electrical performance is as it was at the start of the process. We weigh it, and we ship it to the launch site. And that's NASA's standard process.
I always like to tell people, you spend 4 years of your life, about $100 million of taxpayer money, you build this nice, delicate system, you take these great images, then you go and you kick it, and you heat it up, then you go and you kick it again with the rocket, then you go and scream at it with electromagnetic waves, put it in a vacuum chamber and try to heat it up, cool it down, heat up, cool it down, and then test it. And these are very stressful times, because really at any time you can learn something didn't go well. And so the answer is you try to stress it within reason before you put it in space. You try to put it through at least every environment and everything it's going to see, in space.
Filler question girl. Okay, so I know you guys are really specific to looking at the sun from the coronal side, and more specifically, certain parts that have already been discussed, but maybe you could talk about how is IRIS similar to Hubble, or is it at all, or is there a relationship? I mean, there are satellites that look into deep space. And while I'm up here, I just want to plug a couple of things really quick. Before you leave, don't forget, we do have a gift shop, so if you want to bring something back home to your families about NASA, we'd love for you to stop by. They will be closing at 7:30, not to make you leave, but just to say, hey, we do have a gift shop. But anyway, yeah, if you could kind of talk about if there's any similarity at all to Hubble, perhaps. Thank you.
Well, there's more differences than similarities, but from an attitude control point of view, there's some similarities. The two spacecraft have some similar components. We have four reaction wheels. We're able to point anywhere in 3-axis space. As I mentioned earlier, Hubble has a gyro path which allows it to slew anywhere in the universe that it wants to, whereas IRIS does not. It can only point to the sun with its sun sensors, and that was a choice we made. We both have star trackers to update our attitude, and to help us with roll. We both have magnetometers, which senses the Earth's magnetic field for some of the attitude control modes. Beyond that, the similarities pretty much stop. I think Hubble has what we call a fine guidance sensor. So to do their fine pointing, which is I think about 7/1000ths of an arc second, they use 2 guide stars. So they have a special camera that looks at 2 stars and kind of nulls out the errors, the small disturbances. IRIS has something similar. We have a guide telescope, which we look at the image of the sun. We have 4 photodiodes, and we use the signal on those photodiodes to null out our small disturbances to like about 0.2 of an arc second. So Hubble's pointing is much more stable than IRIS, but they're looking at distant targets. We're looking at the sun, so it's much less challenging. From a scientific perspective, they've got many more instruments than we do. We both have spectrometers. We're actually both looking at the same ultraviolet wavelength bands. Hubble's looking towards the background ultraviolet radiation. They're looking at absorption lines in their spectrometer. We're looking at emission lines in the sun. So some similarities, a lot of differences. It actually, it costs 20,000 times more than ours. 20,000 times, but, they're a great observatory in respects.
A question about, I hear about space weather, and I am assuming that you're looking at the sun to learn more about space weather, but what is it that you hope to learn, or what is it that you're hoping to... You hear about satellites being affected by electromagnetic pulses and things like that. Can you expand on anything like that?
Carl Schreiber will be talking in a few weeks about space weather. What we're doing is providing the data for their modeling so they can further predict, improve their models so they can predict what the sun will be doing. Maybe even someday predict when CMEs or something will happen. So that's kind of our point of it, is trying to understand how the sun impacts. I mean, space weather is how the sun interacts with the Earth. We're looking at, obviously, the piece of it in the sun's region, and there are other missions looking at different parts of it, the corona and other parts. But I don't know a lot about space weather.
I mean, we do take, our computers take radiation hits, so we are susceptible to the effects of space weather, trapped protons in the Earth's orbit. The computer technology is much more advanced, and it's advancing all the time, so we're less susceptible to space weather than used to be. And as I mentioned earlier, we haven't even had a computer reboot. It's been pretty quiet, which is a good sign we have good hardware.
What is the equivalent radiative heat flux that hits the sensors themselves? I mean,
start again. Okay.
The heat flux, when you look at the sun, you have a lot of heat flux coming in. Like I think on ground it's 1.4 kilowatt per square meter. Up in space, it's probably a bit more, and it is focused through the lenses. So the sensors, do they get this heat flux directly, or is it filtered? Or
so the coating, which I couldn't remember what material it is, it's the mirrors. So the primary mirror, which is the first mirror that the light sees, actually passes the infrared part of the spectrum through the glass onto that white collar we showed you. So we only reflect, and we try to reflect mostly just the UV. So at that point, we've already rejected a lot of the heat. And then when it gets to the secondary mirror, we do the same thing. We have another little heat dump there that takes a little bit more of the heat away. So by the time the light goes into the spectrograph, almost all of the infrared energy has been displaced. It's been rejected out through that little collar I was showing you.
So if it's like 1,400 watts per meter,
yeah.
How much actually goes into the instrument? Do you recall that number?
No, I'd have to look it up. But I know even, I can't remember.
You reject a lot.
Yeah.
You pass only just a small amount into the instrument.
We can queue up. Do you have the video of the science ready? We can just show you a few of the images we've taken and kind of and I'll do a very poor job of explaining science, but so hopefully the picture will amaze you and you don't ask too many questions. But, no, that's not. There we go. If you can, so this is a presentation Alan and Title put together. We'll jump through some of it. This mentioned the 6,000 degree visible surface we talked about. The chromosphere is 10,000 K, which is a measure of temperature, and then out into the greater than million degree corona. That's a coronagraph showing you what goes on way past even outside many diameters of the sun.
Is that the comment?
I think that's the comment, yeah. I just want to show you. There's a little pause. This is I just want to see if we can jump. This is stuff I've talked about. Yeah, go ahead and jump a little bit. Keep going. That was the modeling. This is generated from a computer model. Actually, the computer done here at Pleiades. This is millions and millions of CPU cycles. Okay, so this is how Iris works. If you pause for a second. This red line represents what we call a slit. So we actually have a little mirror. We have a mirror, a little tiny scratch down it, and some light's reflected off the mirror, and the little bit that goes down that slit is what enters the spectrograph. So this little bit of light is what you see over here in our spectrograph. And what they can do is, this is an imaging spectrograph, which is, I'm not going to try to explain, it would take a while, but we can actually take the spectrum and recreate images. So what we can do is, at any time, we can recreate images of 3 or 4 different wavelengths simultaneously. So we can watch what's going on in the sun in multiple wavelengths simultaneously. Go ahead and move forward. I want to go to the one where, go ahead and jump forward a little bit. Keep going. A little bit. There, perfect. Go back. Okay, so pause for a second. Okay, play and pause. So what you're going to see here is, this is what's called the spectral lines. That says that's magnesium, too. And what you'll do is, this is very interesting. This is the wavelength here we're looking at. This is one line. And if you go back a little bit, you'll see, as we go through the line, there we go. Perfect, hit play. You'll see the image change over here. And what you're doing is, you're seeing different energies. You're actually looking at different heights. So it's like being able to see through something. And it's a little hard to explain, but you just saw the sun through several kilometers of material. And by changing the wavelength, we can see different energies. And that is, I forgot how many images, but that one picture is 400 slices we created, so a spectrum from 400. And go ahead and show the next one. And this one you'll see the edge of the sun, the photosphere. And you'll watch it. You'll see how, just by changing your frequency a little bit, you see all these different features of the sun. So that's what a spectrograph lets you do. It lets you see these different features at different wavelengths. Your eyes can't see any of this, and this is...
They're also extracting out velocity information of the flow. So if you see in the bottom there, kilometers per second, to the left of the line shows material that's moving into the sun. To the right of the line is material coming out of the sun. So they're able to help them use that information to build their models.
Yeah, so just what Chris said. So if we actually, I don't know if you can scan back enough to replay that. I don't know if you have that much. But so at the beginning, okay, go ahead, play, stop. So the material is coming towards you. So we can actually measure the speed of the material coming towards you, and then go ahead and let it flow. And then stop. Now some of the material is going away from you. So from this one image, these series of images, you can get velocity, you can get features, and so that's what an imaging spectrograph lets you do. You're not just taking pictures, you're actually extracting scientific information out of that region of the sun. And the one thing we didn't actually say anywhere is we see regions of the sun. Unlike SDO, we're looking at smaller regions of the sun so we can get higher resolution. So I just like to give you a little overview of some of the science you can do and just some of the images you can see.
Do you have any more questions, by the way? Anyone? We have time for about one more or two more questions, so here you go.
I'm just curious about computer systems on board the satellite. How many software engineers were involved in developing the software? What languages you use, operating system?
How many software
engineers were working on the software? How many software engineers? What languages did we use?
On the spacecraft bus, we contracted out through an organization in Arizona, Broadreach, and they had primarily three coders, or primarily two, and some other folks that added bits and pieces. On our own Lockheed side, we developed the attitude control software. We probably had three, so we're up to like 6. On the instrument side, probably about the same.
About 3, yeah.
So maybe about 9 total people.
Amazing.
And some it's written in, I don't know.
C++.
Some of the attitude control is actually written in a modeling program, Simulink type software, and then it was converted directly into flight code. So that one, a human didn't actually write the final flight code. It was directly converted. The others, the instrument software was written in C++. I don't know what Broadreach uses.
It's C++, I'm sure.
And then there's the ground-based systems, collecting and processing the data.
Well, like I said, we use ITOS, which is a Goddard-derived product for the primary command and control. But at NASA Ames, they've developed, custom code using Python scripts to pass the data back and forth to get the data to go to Stanford. And Stanford has their own processing software that was developed under the SDO program. So we're reusing a lot of their software from SDO. I don't know much more about the SDO.
And then the scientists developed their own specialized code to study what they're doing. So that sequence I showed you was one of our scientists in our building. I don't know how many months he spent writing that code just to extract that data. So it depends on where along the flow you're talking about. There's different pieces of software touch it.
Okay, thanks.
I'm interested in the Bay Area connections. So Stanford, Palo Alto, and Ames. What else was involved?
Well, so Palo Alto is our group. We built the instrument along with groups outside the Bay Area. Sunnyvale built the solar arrays. So Lockheed Sunnyvale built the solar arrays.
Spacecraft bus, of course.
And the spacecraft bus was built by Lockheed Sunnyvale. What other components? Is there anything else built in this area?
Are you primarily looking for this area?
Bay Area.
The Bay Area?
Some of the scientists are out of the Bay Area too. I can forget something.
It's pretty much it, right?
Blankets were built in Fremont, I think. The blankets were made by a company in Fremont.
And, it's outside of Bay Area.
Yeah.
Our structures are built in Los Angeles, vendor in Los Angeles, but this was bus from East Bay?
The bus, Vanguard built it in LA, and then San Diego was the comm systems. The
antenna was actually designed by a group here at Ames. It was a contracting group for Ames. But the actual fabrication, I thought that was Arizona.
That's Arizona and DevCub.
Well, I just want to thank you guys for coming out. We're pretty much at the close of the event, but I want to make sure you know we do have the second part. Specifically, is going to go over the mission in detail, the mission overview. We talked about the spacecraft. We want you to come back, bring your friends, tell your neighbors, family, relatives who are visiting. We definitely want you to keep us in mind for something to do on a Wednesday evening hump day. On the 23rd, we're going to talk about the mission of IRIS, and I hope these guys will come back and support the next victims who will be on the stage to talk to us about the mission overview. Eventbrite, again, will be your way to get in the door. We want to make sure that you know anytime you're available, Tuesday through Sunday, we are here at the Visitor Center. We'd love for you to come back and check out our exhibits. NASA is celebrating 75 years this year in July, so you want to come back for that. It's a free, open to the public event, all day, 9 to 5. And if you want to talk to them individually, you have time to do so. We thank you so much for coming out, and we hope you will continue to encourage more folks to learn more about NASA. This is our first pilot, again, for having a science cafe, and we expect to have people to talk to you in the LADI mission. We have NASA's Astrobiology Institute who wants to do a science cafe, so we'll probably have something like that in the next few months, if not in the next few weeks, as well as our Orion crew exploration vehicle that will hopefully be the next wave of sending humans to space on the NASA end. So thank you so much. Thank you, Gary and Chris. You guys have been great. If you could please join me in giving them a round of applause. Overview for the IRIS mission spacecraft, so we really appreciate them coming out. And Lockheed's right down the street, so you want to take a look at what we've been doing with NASA and the Lockheed partnership. There's so much more to it than just a few solar missions. So thank you so much, boys. We really appreciate it, and we hope that you'll enjoy some time with them before we close up. Thank you.
Survey.